Hello students, in this class we will discuss about degree of dissociation. 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 It is denoted by alpha. What is degree of dissociation means? Suppose I told you in a reversible reaction, at certain times will come when concentration of the reactant and the product doesn't change with time. Think of the reaction PCl5. I have taken a particular one, PCl3 and Cl2. A time will come when the concentration of the reactant and the product doesn't change with time. In such case, I can say it has attained equilibrium. At equilibrium, concentration of reactant and product does not change with time. Degree of dissociation means out of 1 mole, 1 mole, moles decomposed at equilibrium. At equilibrium, is known as degree of dissociation. Look at here. In this case, I have written PCl5. It was 1 mole, and suppose X mole if decomposed, so whatever stoichiometric coefficient are 1, 1, 1, so 1 minus X, X and X. So in this case, X stands for degree of dissociation. Of PCl5. On the other hand, think of this case. The same reaction I have taken, but in this case it will give you PCl3 and Cl2. You have taken 10 moles initially, and at equilibrium 2 moles decomposed. Whatever be the moles decomposed, that many moles formed over here. You have taken 10 moles initially, but at equilibrium 2 moles decomposes. So in this case, degree of dissociation, which it can be denoted by alpha, is equal to moles decomposed over moles taken. It will be 2 by 10 is equal to 0.2. 0.2 stand for degree of dissociation in this case. Now I will tell you how we can express equilibrium constant in terms of degree of dissociation. Let us look at this reaction. Okay, so degree of dissociation means out of 1 mole, moles decomposed at equilibrium is known as degree of dissociation. Suppose you have taken 1 mole and 3 moles. It was 0. Nitrogen is gas. It is also gas. It is also gas. As the reactant and the product are all gaseous state, it is an example of homogeneous equilibrium. And when the reactant and the product are in gaseous state, equilibrium constant denoted by Kp. Kp will be what? It will be PnH3 square over Pn2 into pH2 whole cube. This is the expression of equilibrium constant, that is called Kp. Suppose at equilibrium, if alpha mole of nitrogen decomposed, let degree of dissociation of nitrogen be alpha. What does it mean? Out of 1 mole, alpha mole of nitrogen decomposed. How many mole of nitrogen will be left behind? 1 minus alpha. In this case, see, whatever be the moles of nitrogen, moles of hydrogen, size of that, if alpha mole of nitrogen react, so 3 alpha mole of hydrogen will react. So at equilibrium, moles of hydrogen left will be 3 minus 3 alpha. And whatever be the moles of ammonia react, double of them will be formed. So 2 alpha mole will be ammonia will be formed. So at equilibrium, moles of nitrogen left 1 minus alpha, hydrogen left 3 minus 3 alpha, ammonia formed 2 alpha. Now I have to find out the Kp. In order to Kp, you should know PnH3, Pn2 and pH2. At equilibrium, all nitrogen, hydrogen, ammonia, all of them are present in the system. So in a mixture of gas, partial pressure is equal to its moles, that is 1 minus alpha, divided by total moles. If I add it, total moles will be 4 minus 2 alpha. 4 minus 2 alpha into P. That is the partial pressure of nitrogen. pH2 will be what? 3 into 1 minus alpha by 4 minus 2 alpha into P. PnH will be what? In this way, Pn2, pH2 and NH3 was determined. Now I will replace these values in this Kp expression to get the value of Kp at equilibrium. Now if I replace it, what I am getting? Kp is equal to PnH3 is equal to what we have found out, 2 alpha by 4 minus 2 alpha into P square. Pn2 is 1 minus alpha into P. pH2 will be what? It's cube. On simplifying, it is 4 alpha square into P square by 4 minus 2 alpha whole square. In this case, it will be 4 minus alpha to the power 1, 4 minus alpha to the power 3. So it will be 1 by, it is 27 into 1 minus alpha to the power 4 by 4 minus 2 alpha to the power 4. This goes to the power. So what we are getting? 4 alpha square P square over 27 into 1 minus alpha to the power 4 into 4 minus 2 alpha square into 4 minus 2 alpha to the power 4. Now cancelling these two, what we are getting? 4 alpha square, it was P square, and the denominator was found out to be what? P to the power 4. P to the power 3 into 3 is equal to P to the power 4. So it is equal to 4 alpha square P square by 27 1 minus alpha whole to the power 4 into 4 minus 2 alpha square will goes up. In this case, it will be P to the power 4. Now what I am telling, as alpha is very less compared to unity, so 1 minus alpha can be written as 1 and 4 minus 2 alpha can be written as simply 4. So if you do this simplification, what we are getting? 64 alpha square P square by 27 into P to the power 4, that is Kp. So Kp contain both alpha and P. So it is what? Kp is equal to 64 alpha square by 27 P square. So Kp and P are inversely related. That is, if P is more, Kp will be less and vice versa. This is the way of expression of the Kp in terms of degree of dissociation. Now I will do one more way of expressing Kp, that is called Kn in terms of Kn. Look at here how I am doing it. Same equation I am taking. At equilibrium, what I found out, 1 minus alpha to alpha. Total moles at equilibrium, 4 minus 2 alpha. Is it though? Now, Kp is equal to what I have done? PnH3 by Pn2 into pH2 whole to the power cube. This P stands for partial pressure because all of them are in gaseous state. It can be written as partial pressure is equal to moles of nitrogen NNH3 by sigma n. Sigma n means summation of n into P. P is the total pressure, H square. Kp is equal to moles of ammonia by total moles into total pressure square. Pn2 will be what? Nn2 into P. It will be NH2 by sigma n into P. Sigma n stands for total moles, sigma P stands for total pressure. Okay. See, this is not yet complete. I will complete it now. Look at it how I am doing it. Okay. In this case, moles of nitrogen I will do in one way, and pressure and summation of the moles I will take in other way. See how I am doing it. You can do it this way. Kp I can written as whole cube into what it will be? P by sigma n. It was square earlier by P by sigma n to the power 4, 1 and 3 denominator. So Kp is equal to del n. Del n stands for moles of reactant minus moles of product at equilibrium. So Kp is equal to, these things cannot be denoted by Kn into P by sigma n to the power del n. Kn is equal to ratio of the moles at equilibrium. P stands for total pressure, sigma n stands for total moles at equilibrium. Del n is the difference between the moles of reactant and product. Now wrongly written, it will be product minus reactant. Moles of product minus reactant at equilibrium. Moles of product, del n better write. Achha, I am writing it this way. Again I am doing it. Achha. Kp is equal to Kn into P by sigma n. Del n is equal to moles of product minus moles of reactant at equilibrium. Okay, this is another way, Kp, and in the case of Kn. Now, when the reactant and the product are in liquid state, in this case equilibrium constant denoted by Kc. How to do that? That part also I am showing it to you. Just complete it, and any doubt Write on the comment box. Otherwise, I am telling you how to do Kc also. Now look at here, another case. In this case, all of them are in liquid state. In this case, equilibrium constant denoted by Kc, not Kp. Suppose the concentration is 1 molar, alpha be the degree of dissociation, or I can take it to be C molar also. Both of them are C molar. Degree of dissociation is alpha. So what is degree of dissociation? Is alpha. What does it mean? Out of 1 mole, alpha mole decomposed, out of C moles, C alpha mole will decomposed. So what will be the amount of acetic acid left? C minus C alpha. It will be C minus C alpha. In this case also C alpha into C alpha. This is the equilibrium concentration of the reactant and the product at equilibrium. If the volume of the container is V, so concentration will be C minus C alpha by V. C minus C alpha by V. It will be C alpha by V. It will be C alpha by V. It is the concentration of the reactant and the product at equilibrium. Now Kc will be what? Kc will be CH3 COOC2H5 H2O, then CH3COOH, then C2H5OH. In this case it will be what? C alpha by V into C alpha by V, C into 1 minus alpha by V into C into 1 minus alpha by V. So it is what? C square alpha square by V square over C square 1 minus alpha whole square by V square. V square cancels, C square cancels. So it is alpha square by 1 minus alpha whole square. This is the case of Kc. Now there is a relation between Kp and Kc. What are the relation? I am showing you the derivation. Look at the derivation, then you will be able to find it. Okay. In Kp, applicable for gaseous state, Kc when they are in liquid state. Now I will establish a relation between Kp and Kc for a reaction. Kp will be the for gaseous one, Kc will be the for same reaction for liquids one. We know in case of Dalton's law of partial pressure, we know Pa into V. Pa stands for the partial pressure of the component A, V is the total volume, Na is its moles of A into RT. So Pa is equal to what I can write? Na by V into RT. Na by V will be the concentration of A. So Pa is equal to ART. Concentration is written in third bracket. So in this case, Kp we have written what? Kp is equal to PnH3 square. For this reaction, I am writing the reaction again by Pn2 into pH2 whole cube. PnH3 you can write this way, concentration of NH3 into RT. So I can write it NH3 into RT. It will be square over, it will be N2RT, it will be H2RT to the power cube, because the partial pressure is equal to concentration into RT, as you see from this relation. On replacing all this value, what we are finding, look at the arrow, I am writing it over here. Kp equals to NH3 square over N2 into H2 whole cube into RT to the power 2 minus 4. These things can be replaced by Kc into RT to the power minus 2. It is the 2 is the step moles of product, 4 is the moles of reactant. So Kc into RT to the power del N. Del N stands for the difference between the moles of product and reactant. Now, a relation between Kp and Kc for a particular reaction will be Kp is equal to Kc RT to the power del N. Kp is the equilibrium constant in terms of gaseous state, Kc for liquid state. R gas constant, T temperature in Kelvin, del N is difference between the moles of product and reactant. Now let us take three reactions. In the first case, see, moles of reactant is 2, moles of product is 3. So for this reaction, 2SO2 is equal to 2SO3 is equal to 2SO2 plus O2. Relation between Kp and Kc will be Kp is equal to Kc into RT to the power moles of product and reactant. The product is 3, reactant is 2 to the power 1. So Kp is equal to Kc RT to the power 1. For this case, what it will be? Kp is equal to Kc RT to the power, in this case product is 1, reactant is 2, that is minus 1. In this case both the way there is 2 moles, so Kp is equal to Kc RT to the power 0. That means Kp is equal to Kc. Hence what is the inference? Inference is that for a reaction when moles of reactant and product are same, then Kp should be equal to Kc. This is the inference which I have come from these reactions. Now I will discuss a very, very important concept, that is, look at the case. Suppose NH4Cl, it decomposes to NH3 plus HCl, or PCl5 decomposes to PCl3 and Cl2. In this case, if the reaction was carried out in a closed vessel, mass of the reactant and the product are same, but as number of molecules changes, it was 1 mole become 2 moles. Hence, due to complete dissociation, as number of moles become double, so observed molecular rate would be half that of expected molecular rate, as due to dissociation number of molecules increases, hence observed molar mass will be half that of expected molar mass. Because the molar mass stands for Avogadro numbers of molecules. In this case, now for 1 mole I am getting 2 moles. Because of that, observed molar mass will be half that of the expected. If 1 mole decomposes to 3 moles, after due to complete dissociation, observed molar mass will be 1/3 that of expected. On the contrary, if it is a case of association where 2 moles gives you 1 moles, as the number of moles become half, observed molar mass will be double that of expected molar mass. Now, if it is not completely dissociated or PCl3 and Cl2. In this case, suppose if it is totally dissociated, suppose M theoretical was your expected molar mass. M observed will be your observed molar mass. Observed molar mass of PCl5 is how much? Phosphorus is 31, chlorine is 35.5. So observed expected molar mass PCl5 will be what? 31 plus 35.5 into 5. 177.5 plus 31 is what? 208.5 expected. If it is totally dissociated, observed molar mass will be what? 208.5 by 2, that is 104.25. Now, if at equilibrium doesn't totally dissociated, a part of them is dissociated, in this case total number of particles increases, hence observed molar mass will be less than the expected molar mass. It won't be equal to 104.25, as it is the number of particles increases, observed molar mass will be less than that of expected, less than 208.5, but 104.25 is the extreme case when all the molecule decomposed. If all the molecule doesn't decompose, it will be more than 104.25 but less than 208.5. In this case, I have to think of the case of your degree of dissociation also. Now I can say how we will derive a relationship between the degree of dissociation observed and expected molar mass. I can do it as follows. Look at here. We know PV equal to W by M. M means your theoretical into RT. In this case, PV equal to what? Mass by molar mass is equal to what? N into RT. If alpha stand for degree of dissociation, in this case what I can think of? Suppose, look at the case, PCl5 decomposes to PCl3 and Cl2. If it is 1 minus alpha, it will be alpha, it will be alpha. So total moles at equilibrium will be what? 1 plus alpha. In this case, if it is for 1 mole, it is 1 plus alpha. For n moles, it will be n into 1 plus alpha. Observed moles, n into 1 plus alpha. So PV is equal to what I can write? W, mass cannot be changed, M observed into RT is equal to what we can write? N into 1 plus alpha. Is it clear? Mass doesn't change, but molar mass changes. So if I divide this equation, WRT, W by M theoretical RT is equal to nRT, and W by M observed RT is equal to N into 1 plus alpha into RT. If I divide these two, suppose it is 1, it is 2. If I divide these two, what we are getting? I am explaining these things to you. W by M theoretical by W by M observed is equal to what we have got? N, in this case N into 1 plus alpha. So M observed by M theoretical 1 by 1 plus alpha. So 1 plus alpha I can write M theoretical by M observed. So alpha will be M theoretical by M observed minus 1. So alpha is equal to M theoretical minus M observed by M observed. This is a very, very important relation for numerical point of view. Try to look at it. If you follow it's okay. If not, I will again discuss it to you. Okay. It's nothing but the case of changes in vapor density or observed molar mass due to dissociation. Because we know molar mass is equal to twice into vapor density. The way molar mass change, in the same way vapor density also change. Very, very important relationship. Today up to this, next we should do more.